In this video, I'll be talking about successive over relaxation method, which is called SOR. This is relevant to the third problem in homework 7. Also example 8.6 of the textbook. So in successive over relaxation method, you're going to look at the equation, the differential equation of this form, d squared phi dx squared plus d squared phi dy squared equals 0. So you notice that in this equation we don't have time. Instead we have y. So still we have two variables, x and y, as independent variables, and phi is dependent variable. So instead of time, now we're going to have y. And then another difference between this equation and the one we saw in previous examples is that here we have second derivative in y, as opposed to first derivative in, let's say, in time before. Now we have second derivative in the second variable, which is y in this case. All right, so let's see how we can solve this kind of problem. We use a finite differencing approach. So we're going to apply central differencing on the first term and central differencing on the second term. Because we have two independent variables, x and y, we're going to use two indices, I and j, similar to the case where we had x and t as time. So I is the index for x and j is the index for y. Now if I discretize the first term, d squared phi dx squared, I'll be getting phi I minus 1 comma j minus 2 phi I j plus phi I plus 1 comma j over del x squared. So this is basically d phi dx, d squared phi dx squared. And then the second term, which is d squared dy squared, d phi squared, d squared phi dy squared. If we discretize this using central differencing, we get phi I comma j minus 1 minus 2 phi I j plus phi I j plus 1. Basically only the index of y, which is j, varies from j minus 1 to j plus 1. In the first term we fix j, and the index over I varies from I minus 1 to I plus 1. All right, so the first term plus the second term is equal to 0. Now here in successive over relaxation method, we're going to solve for the center point, which is phi ij. Okay, so from these two terms, I'm going to keep phi ij on the left side, and then I'm going to move everything else to the right side. Okay, so at the end of the day, I get phi ij on the left side equals to, now you have to multiply through by del x squared and del y squared. So if you do the math, you see that on the right side you get del x squared times this term and that term plus del y squared times this term and this term, which is written here. And then the whole this whole thing divided by 2 del x squared plus 2 del y squared. So 2 is coming from the coefficient 2 up front here, and then del x squared plus del y squared actually is because we multiplied through by del x squared and del y squared. So anyways, from this line to that line, all I did was I solved for phi ij. Now let's assume del x and del y are equal. So if del x and del y are equal, we can simplify del x squared and del y squared from numerator with these ones in the denominator. Okay, so if you do that, we see that phi ij now becomes 1/4. Basically, these cancel out. So well, downstairs you get 2 plus 2 is 4. You get 1/4 of phi ij minus 1 plus phi ij plus 1, which are these two terms, and then we have phi I minus 1j, phi I plus 1j, which are these two terms. Okay, so to solve for phi ij, we need to know these four terms. The way we do in successive over relaxation method is we start with initial guess. We assume let's say we have a box like this, and the horizontal axis is the x-axis and the vertical axis is the y-axis. We discretize our x and y-axis similar to the problem, the heat equation or the diffusion equation we looked at before. Along the x we have some increment called delta x, and along the y we have some increment called delta y. So basically we come up with a grid. For each point we have to solve for phi. Basically ij is a generic point along this grid point, and then basically phi ij is the value of phi along or right at that grid point. So imagine I have four boundary conditions. On the bottom and on the top and bottom I have phi equals 0, on the left I have phi equals 1, and on the right I have phi equals 0. And the goal is, well, I want to solve for phi inside the domain such that it satisfies this second order differential equation, which is called Laplace equation. All right. So this is, if you want to know what this physically means, this is basically if you have a rectangular plate and you apply some voltages around it. In this case, phi has the concept of voltage. You can assume that the voltage is 0 here, 0 here, 0 here, and a voltage equal to 1 here. Then the question is, what is the voltage inside this box? So then you have to solve this Laplace equation, and the solution for phi is actually the voltage at any point x and y. So we start with some initial guess. We assume that on the boundary phis are zeros around these three edges, and then on this edge is 1, which is exactly equal to the boundary conditions we're given. But inside you can assume any value for phi as initial guess. So let's assume all the values are, let's say, 0. Okay, so inside we can assume that all zeros, and then we're gonna solve for phi ij using the 4 values I minus 1j, I plus 1j, ij minus 1, ij plus 1. So this is basically, if you look at this grid, let's say we have this grid, and I'm looking at phi ij here, the value of phi ij here is related to the 4 points across the grid. So basically it needs the value of phi on the north side, on the south side, on the west side, and on the east side. So using these 4 values, we can calculate the value of the middle point. So now, because I initially guessed some values for all points, I can apply equation 2, which we just derived. I can apply it to all intermediate points, starting from, let's say, this point, right, and then go maybe along the x first, then come to the next row, and then go along the x all the way, except the boundary points. Boundary points, we cannot apply this equation because the boundary points are given. And so you can actually sweep across the grid points until you solve for all phi ij. All right. So this is one cycle over the lattice. You have to do that many times unless or until the difference between two successive values, or the difference between the phi old and phi new for each grid point is less than a tolerance. In that case, you can actually stop the sweep. So you're going to see that in more details when I talk about the VBA script in the next video, how we can sweep from top to bottom over each ij point. So another important point here is to accelerate the convergence or make the convergence faster. You can find phi ij from the equation we derived before. So I'm just rewriting this equation again over here. Let's call it uij instead of phi ij. So on the left side I have uij, and on the right side I have same as before as in equation 1. I have phi ij minus 1, ij plus 1, I minus 1j, I plus 1j. This is exactly as I had here. On the right side, I'm going to call it uij instead of phi ij. I'm sorry, on the left side. Now, in equation 2 before, or in equation 1, we had phi ij equal to this term. Now, I called it uij, and I relate this uij to phi ij as follows. I'm saying phi ij is equal to whatever I have in phi ij right now, plus some coefficient, which we call it successive relaxation factor, times the difference of what I had before in phi ij and what I just calculated as uij. Now, if the successive relaxation factor is something between 1.2 and 1.5, you actually get much faster convergence compared to if successive relaxation factor is 1. If successive relaxation factor is 1, basically you can see that you get back to the original equation 1 here. Basically your phi ij would be exactly equal to this. In this video, I'm going to talk about a new method to solve differential equations that is called successive over relaxation, which is abbreviated as SOR. This is very useful in elliptic partial differential equations, and specifically for Laplace equations, which is written as d squared phi dx squared plus d squared phi dy squared equal to 0. Phi is the dependent function, which is the unknown, and x and y are the independent variables. So before the equations we looked at, like the heat equation or diffusion equation, we had two independent variables, x and t, just time. Now in this case we have x and y. Okay. And another difference between the Laplace equation, which is this equation, and the one we looked at before, is that now we have the second derivative on y, as opposed to first derivative on, let's say, time before, which is the second variable. Now in this case we have the second derivative as opposed to first derivative. Okay. Now this equation has a lot of application in chemical engineering, in physics, and so forth. I have a couple of examples here. For instance, you can use this equation to solve for steady-state heat equation. You can use this for finding the flow in a laminar flow, and also you can use this for voltage distribution across a two-dimensional plane. So let's get into the details of it and see how we can solve this equation using the numerical technique that we're going to learn today. So we're going to use finite differencing on both terms, on the first term and on the second term. We're going to use central differencing. We learn how to apply central differencing on the second derivative. So let's do that. Because we have x and y, two independent variables, we're going to use two indices, I for x and j for y. So the discretization of central differencing on the first term turns out to be something like this: phi I minus 1j minus 2 times phi ij plus phi I plus 1j divided by del x squared. So this is the discretization of the first term right here. And then we have the discretization on the second term, which is I comma j minus 1 minus 2 ij plus 1 divided by del y squared. And this is the discretization of the second term. Okay, so then the whole thing equal to 0. Note that in the second term, I is fixed and j varies from j minus 1 to j plus 1. And then the first term, j is fixed and I is varying from I minus 1 to I plus 1. All right, so these are central differencing again. You can look it up on page 83 of the text. So let's consider two axes. We have x-axis with index I and then y-axis with index j. We're going to use some increment along the x called delta x and some increment along the y which is called delta y. Not necessarily del x and del y are equal. So in successive relaxation method, what we do is we're going to solve for the center term, which is phi ij. Okay, so what I'm going to do now is I'm going to keep phi ij on the left.